You ever stick your hand out of a moving car window and feel that push, that invisible force? It's got a name, drag, and it shapes everything, from the design of a supercar to the survival of animals in the wild. In this explainer, we're going to pull back the curtain on the secrets of drag, and I promise by the end of this, you'll start seeing its effects absolutely everywhere you look. All right, so what's our game plan? First, we'll tackle the big question. What is drag force? Then, we're going to dive into the powerful equation that lets us actually calculate it. From there, we'll explore this cool idea of a natural speed limit called terminal velocity, see how the rules totally change for tiny objects, and finally, we'll connect it all back to the world around us.
So to really get a handle on drag, we have to start with a classic physics puzzle, one that goes all the way back to Galileo. It's one of those questions that seems pretty simple at first, but the answer reveals this powerful, invisible force that's always at play.
I mean, think about it. If you were on the moon where there's no air, they would hit the ground at the exact same time. But here on Earth, something is obviously getting in the way of that feather. So, what is it? What's that invisible thing slowing it down? Well, the answer is drag force. You can basically think of it as friction, but for things moving through a fluid, like air or water. The faster you try to move, the harder it pushes back on you. It's the exact same force you feel on your hand when you stick it out of that car window. But how can we actually measure this force, or even predict it? Well, it turns out there's a really elegant equation that physicists and engineers use as their toolkit. It helps them design everything from cars that save you gas to airplanes that fly faster. So let's unpack it. Okay, now this is the crucial point, so lean in for this one. The relationship isn't linear. If you double your speed, you don't just get double the drag. No way. You get 4 times the drag. Triple your speed, and you're fighting 9 times the drag. This squared relationship is the key to understanding almost everything that follows. And here it is, the whole shebang. Now, I know it might look a little intimidating at first, but trust me, every single symbol in this equation tells an important part of the story of what creates drag. Let's break it down piece by piece. We've got C, the drag coefficient, which is all about the object's shape, how slippery it is. Then we have rho, that's the Greek letter, which stands for the density of the fluid you're moving through. A is the frontal area, how big of a target you present to the fluid. And finally, v is velocity, which we already know has that huge squared impact. And this is where it gets really fascinating. Just look at the numbers on this table. An airfoil, like a plane's wing, has a drag coefficient of just 0.05. Now compare that to a Hummer H2 at 0.64. That is a massive difference. It means the Hummer has to use way more energy just to push the air out of its way. This single number is why car designers are absolutely obsessed with aerodynamics. So, since we know that drag increases with the square of speed, it brings up a really interesting question. What happens when something, like a skydiver, just keeps falling for a long time? Is there a speed limit? You have to imagine this as a battle of forces. Gravity is pulling the skydiver down with a constant force. That's just their weight. But at the same time, drag force is pushing up, and it gets stronger and stronger and stronger as the skydiver falls faster and faster. Eventually, you get to a point where that upward push of drag becomes exactly equal to the downward pull of gravity. The forces balance out perfectly. The net force becomes 0. And according to Newton's laws, if there's no net force, there's no more acceleration. The skydiver has hit their maximum speed. They've reached terminal velocity. And to put a number on that, get this. For a 75-kilogram skydiver in a head-first pike position, trying to be as aerodynamic as possible, that terminal velocity is a staggering 350 kilometers per hour. That is faster than many sports cars can even go. Okay, time for a quick check-in, a little pop quiz. Let's say 2 skydivers jump at the same time, in the exact same body position. One weighs 60 kilograms, the other is 90 kilograms. Based on what we just learned, who's going to have the higher terminal velocity? Think about it for a second. If you said the heavier 90-kilogram skydiver, you are absolutely correct. Nailed it. It's because they have a greater weight pulling them down, right? So they need to reach a much higher speed to generate enough of that upward drag force to finally balance it all out. But is that squared relationship the whole story? I mean, it works perfectly for big, fast things like us and cars. But what happens when we zoom way, way in to the world of the microscopic? Do the same rules still apply? Well, it turns out for tiny particles moving very slowly, like a speck of dust in the air or a bacterium in water, the physics actually changes. The drag force is no longer proportional to velocity squared. It's just directly proportional to velocity. So if you double the speed, you just double the drag. Simple as that. This linear relationship is described by something called Stokes' law. And notice here, the velocity v in this equation isn't squared anymore. This law is absolutely crucial for understanding how things move through viscous fluids. Think of something thick, like honey, or even just water when you're at that microscopic scale. This is exactly why dust seems to just hang in a sunbeam instead of dropping like a rock. Its terminal velocity is incredibly low. A bacterium might have a terminal velocity of just 2 micrometers per second. To that bacterium, water feels as thick as honey does to us. So we have these two laws, one for the big and fast, and one for the small and slow. Let's finish up by seeing how this invisible force has a very, very visible impact all around us, in both the natural world and in our own technology. This famous quote from the biologist J.B.S. Haldane just captures the idea perfectly. A mouse has a really large surface area compared to its tiny weight. This means it reaches a very low and very survivable terminal velocity. For a person or a horse, it's a tragically different story.
And once you start looking, you see that both evolution and human engineering are in this constant battle against drag. The bodies of fish are perfectly streamlined. Race cars are basically shaped like upside-down airplane wings. Even migratory birds flying in that V formation, that's all about reducing drag for the flock. It's a fundamental principle of efficient design. So the next time you see a flock of birds or a sleek sports car or even just some dust dancing in a sunbeam, you'll know the invisible force that's shaping what you see. Drag isn't just an obstacle, it's also a master designer. Now that you know its secrets, what examples of its influence